All right, good afternoon. We're going to finish off the rest of section 12.1 today. We got started with it yesterday and we're just going to finish off today. And just going through a couple things we talked about briefly yesterday, so if anyone was absent, they can kind of catch up. Plus, this will just refresh everybody's memory as to what we were up to. First, we were talking about a new shape that we called yesterday a polyhedron. And the idea here was polyhedron aren't going to be two-dimensional, but they'll be three-dimensional. And they'll be made up of all of the faces of a polyhedron are polygons. So a polyhedron will be made up of polygons. So things like triangles, quadrilaterals, pentagons, hexagons, and so on. So the two shapes I've taken a picture of, the first initial question would be, is each one a polyhedron? If I call this one number 1, the answer here is yes, because no matter what face you look at, every face of this shape is a polygon. The sides coming up to the point of the pyramid are three-sided, so therefore they're triangles. The polygon that makes up the base has 1, 2, 3, 4, 5 sides, so therefore it's a polygon. And you keep looping around no matter which which face you look at, everyone's a polygon. But the second shape, if I call this one number 2 over here, this one's going to be a no, because the faces of this do not form polygons. The most obvious one would be the circular base. You don't have to even go any further than that. A circle is not a polygon, so therefore this is not a polyhedron, using the new term. Okay? But we talked about some of those yesterday, so hopefully that's not too big of a deal. And then the other thing I'd like to review quickly is the definitions for the different pieces that make up a polyhedron. So I just want to refresh everybody's memory. We're mainly going to concern ourselves with 3 definitions, 3 parts for every polyhedron. We're going to be worried about a face, we're going to be worried about what are called edges, and we're going to be worried about vertices, or individually a vertex. Now, if you remember, the face of a polyhedron are the individual polygons. So I'm just kind of abbreviating here. But each face is one of the polygons. An edge is where 2 polygons, that's bad handwriting, where 2 polygons meet. And then a vertex is where 3 or more edges meet. Where 3 or more edges meet. Okay, and so one of our challenges is going to be to count the number of faces, the number of edges, and the number of vertices that a polyhedron has. Okay? All right. So the idea might go something like this. The very bottom, the base of this pyramid would have, let me choose a color here that stands out, would have 1, 2, 3, 4, 5, 6 sides. So that base is one of the faces. It's a hexagon. But then every side from that hexagon that goes up to the point, the apex of the pyramid, is a triangle, and because the base has 6 sides, there'd be 6 triangles that are going up to the apex of that pyramid. So one base, 6 triangular sides, would give us a total of 7 faces. Okay? The number of edges then would be where all of those triangles meet, right? So 6 triangles would meet on 6 edges, plus there's 6 edges around the hexagon at the base, so 6 plus 6 gets a total of 12. And then the vertices are where all of the edges come together, and I could choose a different color here that might stand out a little bit. So we'd have all of these vertices around the base, so 6 altogether, plus the one at the top, giving us a total of, giving us a total of 7. And if you remember from yesterday, Euler's formula, oh, actually I used the wrong word, Euler's theorem, sorry. That once again said that the number of faces plus the number of vertices has to be equal to the number of edges plus 2. And you can check it. So you can take our number of faces, 7, our number of vertices, 7, our number of edges, 12, and essentially ask the question, is that true? Well, obviously, because 14 is equal to 14. So we know we counted correctly. Okay? So let's just try a couple more of those just for a little bit of practice. All right, here's another polyhedron. It's a polyhedron because every one of the faces is a polygon. All right, and what we're going to ask you to practice again is counting the number of faces, the number of edges, the number of vertices. All right, the faces again are the polygons. And on the end of this son of a gun, the end of this shape has 1, 2, 3, 4, 5, 6 sides. The polygon on the other end has 1, 2, 3, 4, 5, 6. So each of those, of course, is a hexagon. And since they each have 6, that means there's going to be 6 quadrilaterals connecting. All right, so 6 quadrilaterals connecting the 2 hexagons, so that's a total of 6 plus the 2 ends. You have an end over to the left and an end over to the right, so that gives us a total of 8 faces. Okay? Then the edges would be the 6 that make up the hexagon on the left side, the 6 that make up the hexagon on the right side, and then 6 lines that connect them side to side, so 6, 6, and 6 gives us 18 edges. And then finally the vertices, be all these places where these edges come together. So there's going to be 6 on that end, 6 on this end, so 6 plus 6 gets us a total of 12. Okay? And once again, Euler's theorem says faces plus vertices has to be equal to edges plus 2. And let's just check ours works. 8 faces, 12 vertices, and 18 edges. 8 plus 12, 18 plus 2, check. So we know we've counted correctly. We know we've counted those up correctly. Okay? And one more, just quick one. You could probably skip over this one on your video using the sliding bar if you'd like, but just jog through one more, again, counting faces, edges, and vertices. Okay, so if you look at the top or the bottom of this thing, the top 1, 2, 3, 4, 5, the bottom 1, 2, 3, 4, 5. So we have pentagon on the top, pentagon on the bottom. That means all of these sides then are quadrilaterals. And because the top has 5 sides and the bottom has 5 sides, that means connecting those are going to be 5 quadrilaterals. So 5 quadrilaterals around the side, plus the top, plus the bottom, gets us a total of 7 faces. Okay? The number of edges, the top is made up of 5 sides, the bottom is made up of 5 sides, and there's 5 vertical lines. So 5, 5, and 5 is 15. And then the vertices, we have 5 vertices around the top, 5 vertices around the bottom. So 5 plus 5 gives us a total of 10. And once again, Euler's theorem says faces plus vertices has to be equal to edges plus 2. Let's see if ours works. 7 plus 10, is that equal to 15 plus 2? And you can see, yep, it does work out, that checks. So we know our count has to be correct. Has to be correct. Okay? All right, so just a few more of those like we talked yesterday. Then a couple of new definitions, but similar to ones you know from way back in the first part of the year. Early in the year, we talked about convex and concave polygons. And back then, a polygon was called convex if you could connect any 2 points anywhere in the polygon and the line doesn't go outside of the polygon. So if I connect this point with this point over here, the connecting line does not go outside of the polygon, so it's called convex. Concave could be something like this, where connecting a point here to a point here, the connecting line has to go outside of the polygon. So we call that concave. Well, we have a similar situation with polyhedron. If the connecting line stays inside of the shape, it's called convex. But if it ever can go outside of the shape, then it's called convex. So if it stays inside, convex. If it goes outside, if it can possibly go outside, then it's called concave. Okay, so here's just a couple of easy examples. All right, I doubt I'm not sure you have to draw any of these out because they're pretty tricky to draw. You can try if you'd like, but the idea just simply, are they convex or concave? All right, so we just try to connect points. We get a little bit pickier when they're solids. Usually we talk about a point on a face to another point on a face. Not that it matters too much, but if I pick this point on the front with this point over on the side and connect, that line has to stay inside. It has no choice. So therefore it has to be convex. But if I were to choose this point and connect them, that line is going to be outside of the star-shaped thing, and so therefore that one's going to be called concave. And then any point here on the surface to any point down here, you have to imagine the connecting line would stay inside, so therefore that's called convex. Okay, so those would be pretty easy, pretty obvious. When you see examples, those are pretty darn obvious, which you're going to have, which you're going to have sitting in front of you. Okay? All right. And then finally, the last thing that we're going to talk about are what are called cross-sections. And here the idea is we're going to take a three-dimensional object, and let's just take something nice and easy that I can draw by hand. So here's something that we'll later call a prism. Right, you wouldn't be able to see that side. So pretend that's a triangular prism, triangle on the front, triangle on the back, connected by quadrilaterals. Okay, and what we do with a cross section is we intersect a polyhedron, so a three-dimensional solid, with a plane. And remember, in geometry, the word plane means a flat surface. It means a flat surface. Okay? And so what we could do is we could insert a flat surface. I'll do it and try to do it in a different color. And we can do this, of course, in a whole variety of ways. We could try to insert the plane kind of through the middle of the shape, so it hits right through the middle of the shape, right? And what we're going to question you on is, what would the shape be for the cross-section? What would the shape be for the cross-section? Okay? So let's give it a try on a couple of examples where I've got some pictures. And again, the question is going to be, what would be the cross-section? Okay? So here we originally have a three-dimensional object that's a pentagon on the end. Okay? And then we put a plane through it, kind of parallel to the base. And our question is, what's going to be the cross-section? So for me, it's pretty easy with these colored pencils because I can just trace where the plane would intersect the polyhedron, and then you can just simply count up the number of sides, and you can tell from this one that what we'd have is a quadrilateral. We just simply have a quadrilateral for the intersection of the original shape and the plane. Okay, other times, well, this one I guess isn't too much more difficult. This one's a little trickier maybe. But again, with one of these colored pencils, I could outline the intersection. Notice it's that same pentagon on the end as the previous one, but we just tipped the plane over. We just tipped it at an angle. So obviously the intersection is still four sides, so the instinct is to say, well, it's a quadrilateral. But we could probably go a step further because it looks like this lowest side and this highest side looks like they're parallel to each other, but they're different lengths. They do not look like they're the same length. So we could probably adjust and call that also a trapezoid. Okay? And the final one here, I think this is my last one. We have that same darn shape. It's that same solid that has the pentagon on the end. But this time we've tipped the plane at a kind of a weird angle. And again, I'll outline the intersection. And when I outline the intersection, you can tell, of course, what we have is just a three-sided intersection. So therefore, of course, our cross-section would then be a triangle. Okay, so the artwork in the book is actually pretty good. So it makes it fairly easy to kind of keep track of what shape the points of intersection will be. Okay, so that's it then for section 1. You should be all set to go to finish off the rest of that section, doing the rest of the assignment. We'll go over questions on this one Thursday, turn this one in, and then we'll get ourselves started on section 2. Okay, so hope you're having a good day, and we'll see you on Thursday.